Hello everyone, welcome to the fourth lecture on deep learning. Today we're going to be looking at a theory of generalization, how we can design deep neural networks on some data so they learn a distribution over that data, but so that they can generalize to new unseen data. So typically you have a training data set which has been collected under some conditions, maybe from a couple of countries, but then you want to test it and you want it to generalize to new unseen data, maybe from different countries or different conditions and environments. So we're going to be looking at how we can do that and how we can effectively design models and what kind of functions we choose and the scientific approach we use to design deep neural networks. So in this lecture we're going to start by discussing how deep neural networks can approximate any function. So we have some kind of assurance that they can actually fit to the data. But then we're going to look at some of the theory behind how they generalize to unseen data. So we'll be looking at ways to improve their representation ability and capacity. So looking at kind of what functions we choose to put into our deep neural networks. And this will involve studying some of the very popular design patterns and components that we'll see in state-of-the-art deep neural network architectures. And lastly, we're going to examine effective strategies of regularization to ensure that the models will well capture the data distribution. What does regularization mean? Well, normally we'll have very over-parameterized deep neural networks, but we'll want the functions they learn to be quite smooth and well fit to the data. So this kind of approach here. So at the end of this lecture, you should be in a much better position to design an architecture for a given dataset and task. So by the end of this lecture, you'll know the foundational theory behind generalization. And by the end of this lecture, you should have several more tools now available in your armory so that you can tackle and build models that generalize well. So I'm going to start this lecture with just a quote, and the quote is, "The ability to deal with overfitting is what separates professionals from amateurs. Everyone can fit, but if you know exactly what overfitting is and how to deal with it, then you have an edge that someone who doesn't know the fundamentals won't be able to comprehend." So that's the end of the quote. And I think that's quite an important quote. When many people start out in the field of deep learning, they just get some code off the internet, they start training it, they run it, they get like 99 test accuracy or training accuracy, and they're super excited and they think, oh, I've built this neural network which is like gets 99% on my test set or on my training set, and it's like amazing, it's gonna like do everything and solve all of these problems so well. And then they find that in the real world, when it's deployed on a production grade server and it starts seeing data from different distributions and different users start to interrogate the model, then things all fall to pieces and it doesn't work at all, and it gets 0% accuracy and they have no clue why and what's going on. So hopefully this lecture will sort of shed some light on what's happening. So let's start off with like what's called the universal function approximator theory, just for networks of arbitrary width. So this is where we have a shallow neural network, but we're allowed to have as many neurons as we like in it. And this theorem basically states that this class of neural networks can approximate any function. So let's have a look. And this is really kind of a visual proof of it here. So this is like a feed forward neural network with a single hidden layer. So we've got this, it just goes forward. It doesn't have any funny bits in its architecture where it's got cycles or anything funky. It's just got this single hidden layer. And it's got this finite number of neurons here. In this case, just the example, we've just got, 5 or 6 neurons. So a very small number of neurons. And we're going to see that it can approximate any continuous function. So here's an example function on compact subsets of Rn under very, very minimal assumptions on the activation function. So for a wide class of activation functions, in this case, we're just using ReLUs. So in this example, we have this continuous original function. It's f of x equals x cubed plus x squared minus x minus 1. You can just about see that blue curve plotted on the graph over the plus minus 2 domain here for x and y. So if we just train a neural network with this single hidden layer here, and it's got something like 5 or 6 neurons in here, and one output here, using just ReLU activations, we obtain the following weights on these edges and biases on these edges. So if you remember the function of an artificial neuron, it's just you take the weights matrix, all of these weights, you multiply it by the inputs, and then you add on the bias terms, in which case we've just got -1, -1, 1, and 1 for the biases here. We get this, this is what you would get, this is the value as you get, The values are shown also in red here. And we can see that when we actually graph this function, f of x, that the neural network's learned, it well approximates the underlying blue function with just a small number of neurons. And as you add more neurons, you'll get better fitting of data, more of these kind of piecewise linear functions. So that's kind of a visual proof behind how it works, and you can just see intuitively, yes, how it can fit to any kind of function with the more, as you increase the width of the number of neurons you have. So what we're kind of interested in is, well, that's all great, and it's a nice toy example, gives us some reassurance, but what about depth? What about going deep? What if we had the case where instead of allowing us to grow wide with just one layer, what if we constrained the width? So we had a fixed width, but we're allowed to have arbitrary depth. Well, does the theorem still hold? Can we still have assurance that deep neural networks do actually generalize? And very, very recently, just this year, Patrick Kidger is a young and enthusiastic PhD student from Oxford, recently submitted this summer in 2020 an improvement of the theory of how deep neural networks of bounded width can approximate any function. And there's a very nice, very short YouTube video. If you're interested, you can check it out, by Patrick. But just to kind of explain visually with a visual proof again, the first thing the neural network can do is it can copy its inputs via the identity function. So it can just learn to copy inputs. You can have the activation just directly just be the identity, so it can take any inputs and copy it to the next layer. And then you've got this, that gives you this small amount of computation, which you can see in the light blue arrows here. And that can be accumulated into the kind of darker blue arrows the same way as the arbitrary width proof. So you can kind of extend that proof. And while the proof does give us confidence in deep learning, at least it's equivalent and it can still approximate any continuous function, it doesn't really give us much insight as to why in the expected case, e.g. with natural signals and functions that occur in network, it's actually better. But it does give us that reassurance that it does actually work. So we do actually need to dig a bit deeper, excuse the pun, to see why deep learning is effective. But still, it's very nice to have these kind of reassurances that yes, it does hold. So what is it exactly that we want? Well, from a probabilistic perspective, we can taxonomize the learning problem into one of three classes. We can have, here they are. So we can have estimating the probability of y given x, or conditional on x, and you can say this kind of class of models are discriminative models, like classifiers. And here, y would be like your target classification, whether it's cats or horses or dogs, and x would be your inputs, like your images or your spreadsheet data or whatever. And then y is basically what we're trying to predict is this probability. So we really want the probability mass function of whether the model estimates whether it's a bird, a cat, whether x is a bird, a cat, or a dog. So from the classes that we're trying to estimate. So that's just estimating like this discrete set of classes, this discriminative model, which classifies what the probability of the class conditional on the data. The other type of model you can get are generative models, and these kind of fall loosely into these two secondary classes. And the first one here is what is often referred to as conditional generative modeling. So this involves predicting the data, trying to estimate the data, conditional on some other signal. And that other signal could be, for example, previous data. So if you're doing like time series forecasting, predicting the weather, predicting stocks, you condition it on past information, so past weather of previous days. So it could be like the census signal over the last week. Or you could think of it like we want to predict an image of a face, but conditional on some probability mass function or other distributional data, which could be things like the age and the gender. So it's like, given the age of a 30-year-old female, what is the distribution of faces that look like that? And y can be just like any multivariate probability density function. It could be anything you like, really. It could be geographic coordinates. It could be just any extra data which helps us refine that distribution over X that we want to estimate. So that's conditional generative modeling. And then the third class is like the more general case, really, and that's also generative modeling, but this is learning the joint distribution between X and Y. And this is really the holy grail of deep learning. It's estimating the joint distribution of the data in an unsupervised fashion. So, for example, you might have a data set containing images of stars, and you can imagine just looking at all of the stars in just like lots of images. And we want to learn how do we fully generate that data set. And if we can learn how to perfectly replicate that data, then we have truly learned to understand the laws of physics and how the universe was created. So we truly do learn the patterns of nature if we can learn this joint distribution over the data without any extra information, if we can perfectly generate that data, get all of the positions of all of the stars perfect, all of the subtle effects of lensing and all of the physical phenomena we'll see. If we really can generate that, then we've somehow actually learnt the underlying rules which govern it. So this kind of is the three types of learning effectively, and the three things we generally want to do in this field. And it all really boils down in the end to just fitting to a probability distribution. So I'll use a 1D illustration for this, but you can imagine this in like 2 dimensions for bivariate distributions, or n dimensions for multivariate distributions, such as distributions over the images and text data. So in this example here, the blue probability density function represents the target that we're trying to estimate. And the red line here is an initial estimate of the initial estimate outputted from our deep neural network. And no matter what inputs you give a deep neural network, you're always going to get some output in this red function here. So just take any deep neural network, it's always going to just give you something. If you put something into it, you're always going to get something out of it. They're generally deterministic. So we're always going to get some prediction. So for any input x on the x-axis here, we can evaluate our red neural network. So let's just say we take a line here. We can always just look at the differences between the two, and we can evaluate it that way, and we can compare it. So what we want to do is minimize this distance between the two lines. So we want to learn to map this red prediction onto the blue line of all of our data. So yeah, just looking at the slide, we want to find or design a model f of x with some parameters theta, and optimize theta such that the red curve f of x with the parameters is equal to the blue curve g of x. And if we minimize the distance between those two functions over the entire space of inputs, you'll see this is just equivalent to minimizing the area between the two curves. So we want this area to be 0, effectively. And the distance measure you use to do this can really be any function you like, whose global minimum is at the origin, where the target functions are identical. So for example, it could be like an L2 norm or an L1 norm, mean squared error or Kullback-Leibler divergence. And yeah, you can just try it between any two normal distributions. So I might be able to just graph something out from Desmov's. Let me see. So here we have a kind of really simple example. I have this equation here, which is the Kullback-Leibler divergence. So it takes these two distributions, and as they become identical, you'll see that the output measure, this value here, goes to 0. And you can really have any function you like in here, so long as it goes to 0 where the two functions are identical to each other. I'll try and match it as best as I can, so you can see it gets lower and lower and lower. So another common measure we'll see is the 0, 1 loss, which is just a function that outputs 0 where the target data is the same as the input, and it just gives 1s everywhere that the signals are not the same. So that's all great, right? Problem solved. We can just take our deep neural model, get the output, and we can just integrate the loss over the data space and adjust the parameters via backpropagation to minimize this loss. Nope. So we can't actually do that. There's this big problem. The big problem is, and this is like related to bias in AI and all of the issues currently around that, which is that we can't observe all of the data space. So if we're training like to generate faces, for example, your data set probably won't have many faces from Ghana in 1573. And it certainly won't have faces from Mars yet in the year 2073. So that's because the expected data we're going to be receiving is from the internet, which has these inherent biases, but the actual full signal of the data, that blue curve that we really want, is all of data over all of space-time. So it's going back to historical data all the way to future data, which we definitely can't observe yet. So if we're training on the stock market, we just have a very small number of samples based on the current time, and maybe we have some of history, but we definitely don't have the full history either. And there's no way we can observe the stocks 1 year into the future. So if you imagine these red squares, these samples we have of our blue function, in the diagram, they're like our current observation of stocks. It's very difficult to estimate the shape and smoothness of the function outside of the known observations going into the future. We don't know whether, how coronavirus is going to necessarily evolve, or whether there's going to be something else a few years down the line which is even worse, or whether things are all going to stabilize. We just can't make those kind of predictions very well. We have this limited horizon of observations. Maybe tomorrow there's going to be another financial crisis. Maybe things will start getting better. But the point is we just cannot observe this data distribution, and we can only observe a small, discrete subset of samples from the data distribution. So what do? Well, we admit defeat. And we first say we can't compute that integral, or its expectation, which is the average error over the entire data space. And therefore what we do instead is we minimize an empirical estimate, which means based on our observations. So we learn instead based on an average of what we do see. You can kind of see this red line here. We kind of average the red that we do see. And then what we say is we just don't care about what's outside of these observations, because it's so unlikely that we'll ever observe them anyway. And that's generally what happens in deep learning. We can do better, but this is the general approach. So when we try to minimize the empirical risk, we're basically just saying we don't care about the parts of the data distribution that we can't observe. And in this case, those other parts of the function are just not considered important. And this is really central to deep learning, and it contributes to one of the main reasons that deep neural networks are often perceived as biased, racist, or discriminatory, etc. And that's not to say this is the only reason for bias in AI, which is a more complex topic for discussion, and something which requires an understanding of the additional distribution of societal bias. We can discuss this more later if you like, but this is certainly a significant contributor to what you're seeing here. So the main takeaway from this slide is that, unfortunately, deep neural networks cheat. In the diagram, we don't fit to the parts of the signal outside of the function. We're terrible at fitting to the tails of the distribution, because it's so unlikely that we'll actually observe those parts of the distribution. Indeed, actually, often it's impossible to observe them due to constraints of our fundamental laws of physics, such as actually estimating far into the future. So if you're part of a minority group and the data set is not collected in a way that is representative of your demographic, then without specialist techniques, which we'll come on to later and we can discuss in more detail later, then the majority of naive deep learning models will unfortunately not fit well to your parts of the signal. So if it's trained with discriminatory behavior, for example, with data collected from Reddit, and if the discriminatory behavior is one of the predominant characteristics under the expectation of your observations, then without designing a specialist model to address this issue, the model itself will be inherently discriminatory under the expected behavior. So yeah, just simply, you can see this as just fitting this estimate to the observations we have, and in the general case, without any additional sophisticated techniques like transferring between domains and doing advanced research into sharing characteristics that we know, or integrating prior information that we know about the tails of the distribution, we get this very biased fit, because we cannot possibly observe data for the tails of the distribution going far into the future and so on beyond the horizon. So noise in the dataset also plays a very important role in this, but I'm not going to dwell long on it because it's less of an issue in the stochastic processes, and we'll uncover more of the story that supersedes this when we examine double descent graphs in regularization in just a few slides' time. But basically, it's difficult to know what parts of the signal are actually noise and what aren't noise, which means that we may end up actually overfitting our data to the noise, and that might result in poor generalization. But we're going to come into this a little bit more rigorously in a minute. So here's where things kind of start to get interesting. When we talk about the idea of collecting a data set from some underlying space or distribution of data, and then the sampling or the collection process itself follows some underlying subset distribution. So try to imagine all the data in the entire world is represented by this blue wavy function here. And now imagine like a local supermarket hire you to build a classifier of their food products for some app that tells the customers about the product information. So you go to your local Durham supermarket and you take like 100,000 photos on your Samsung phone, and you train this classifier to 99% accuracy, so it fits the observations perfectly. And the supermarket management team, they're really happy with you, and they convince their shareholders to roll out the app for the rest of their branches. And then in Japan, for example, customers start using the app, and guess what? It gets 0% accuracy. This is a common problem. Why does this happen? Well, because nearly everyone in Japan, let's just say, uses iPhones, and maybe they take very different photos than the Samsung ones in your dataset. The lighting may be darker in the stores. Maybe people prefer to take photos in portrait rather than landscape mode. And all the packaging and the branding itself is different in the products in Japan. The product range itself is completely different. And let's face it, the sushi over there is far better. But of course, all the writing on the product labels that your model has somehow learned to read is now all in Japanese. So referencing this diagram here, if you imagine fitting your model to the red points, so just imagine like doing a naive estimate of the red points here, you'll probably get this nice kind of diagonal linear function. Imagine just drawing a line straight down these red points here. Maybe just a line just here where my mouse is. But you can see that this line is going to be nowhere near the green estimates here. It's going to sort of go down to, and it's going to think that the values of the data are somewhere down here, but they're actually all the way up here. So they're nowhere near where the actual data is, as if you had trained your model in Japan. So your estimates are just way off. They're completely wrong. And technically or mathematically, what we would say is it doesn't generalize because the two distributions are not IID. They are not independent and identically distributed to each other. If they were IID, then the two sets of points here would project into similar locations of the data distribution. So the data really needs to be sampled in a way that is representative of the task. The training data set needs to be IID to the testing data set. This has massive implications of how you would do data science, and I'm sure you've probably heard this from last year, just in terms of how you would go out into the real world and sample a data set which is representative of how you would expect it to be experienced. So this kind of brings the story into our next chapter, and we can ask ourselves the question, what is the best model? So consider this red step-like or staircase function here as one data distribution of data, and then consider the smooth dashed blue function down the middle here as another data distribution. So maybe they could be data collected in different ways or so on from different places. It's quite trivial to see and prove that the optimal function that fits those two distributions are very different. So for example, if we had like some simple cubic function for the blue line, that would be the best one which fits this blue data distribution, just some small, smooth, simple cubic function. Whereas you can see that the optimal function which fits this red staircase would probably be some piecewise linear function, for example, by rounding some slope of x. So they're very different functions. You need to actually fit them perfectly. You need different maths in your, you need different functions, which brings us on to this idea that there's no one size that fits all. Okay, so there's no one deep neural network architecture which will get you the best solution for your coursework. There's no one. I can't just say, oh, here's the latest paper, it's going to solve all problems optimally. This is like called the no free lunch theorem. There's no single deep neural architecture that will outperform all others in all data sets. You won't be able to just take anything and solve it for everything. Hence there's no free lunch. And it's quite easy to see why that's called the no free lunch theorem, and it's very trivial to prove that theorem. However, that doesn't mean there isn't a scientific approach for designing neural networks for given tasks and data distributions. Actually, it's quite the opposite. First of all, we can see that the optimal solution for a given dataset is actually the simplest solution. And that's called Occam's Razor. So if we've got like multiple hypotheses, or considering a set of all possible neural networks, H, so imagine you've got like this space of all possible architectures out there, deep neural network architectures. What this says is that we prefer the simplest one. And in the case of deep learning, the simplest one is actually the smoothest one. It's the one, if you've got like, for example, for this cubic function, you've got these alternative variants here. It's the smoothest one that fits the data. So from all of the alternative functions, it's the middle one, the central one, the smoothest one. So let's take a sort of deeper look at Occam's Razor and consider a data set with 4 observations sampled from some underlying wavy distribution, maybe a cubic function. So I'm just going to like turn to my notes now and draw this. So if I just move that down, switch over. Hopefully you can see this okay. So if I just start out with, let's just start by taking some data here. We'll just have a function with one parameter, so we'll say theta is one parameter. Let's just like optimally fit our deep neural network to this data. So we'll just draw this red line here. And now we're going to increase our parameters slightly. So we're going to take the same data. Okay. So theta, by the way, here was just determining the angle here. Now I'm going to add another parameter and say we can also change theta, or the slope, but also like the height of the function. So we can also now choose this, whether to increase the slope here. So we can choose the angle and the height. Now I'm going to fit it, and I'm going to say maybe this is now the best fit. So I've changed the height, and I've got this theta here, this angle here. And that's the best fit we can achieve. Now let's now have more parameters, and say like, let's say we've got now available to us a degree 4 polynomial with 4 parameters. So if I just draw the data again, okay, I'm going to try my best to draw a degree 4 polynomial fit to this data. So something like this, maybe like this, like this. I don't know, maybe it comes down here, something like that. That's a perfect fit with a degree 4 polynomial to the data. And you can see like here, with the same number of parameters as the data, we can fit exactly to the data. We can do this perfect fit. So it's got what's called low bias, because it perfectly fits the data. However, if you just imagine this function I've been drawing, it's got high variance. I don't have any other colors on me. Maybe I can just grab this. So imagine like the other data is something like this in blue. You can see it actually fits poorly to other observations. So it's got high variance. It's actually a bad fit to unseen data. So let me just do one more example. So that's with 4 parameters. What if we just crazily increase the number of parameters? So say to 40 parameters. So I'm going to now fit a degree 40 polynomial to that data. So the underlying signal is, as we saw before, but we've got these 4 observations of our blue function, and I'm going to fit a degree 40 polynomial to it. And a degree 40 polynomial is going to look something like this. Very smooth here. Something like that. It's very sharp corners you can take now here. Okay, and now if we plot our underlying data, maybe something like that. So now we have low bias and low variance. Low bias, low variance. So you could actually quantify the gap between training and testing through 2 areas of statistical learning theory, which are called Vaptych-Shemenenko's theory and also the Rademacher complexity. However, I'm not going to really go into the theory of that, as I don't think the bounds that they provide are that useful in deep learning, and it doesn't really offer us a complete picture of this idea here, which actually this introduces something called the double descent graph, and it's quite a nice model of this idea of model capacity. So just going back to the slide here, this is really showing what happens as we increase the capacity of our network. So the red graph is basically the bias here, and as we add more and more parameters, we can perfectly fit to the data. It reaches this green dashed line, which we call the interpolation threshold. Okay, and you saw that in the notes where at 4 parameters we perfectly fit to the data. But as you fit to the data, you also get to this worst point where the variance is maximized, and that degree 4 polynomial you saw had that very poor fit to the other data which it hasn't observed before. So you've probably seen this idea before, where as you have a higher and higher capacity model, you get this graph where the variance decreases initially, but then it starts to increase as you overfit to your data, and as your dimensionality reaches that of the data as you perfectly fit it. But the full picture has what is called this double descent graph, whereas you keep adding more and more and more and more capacity, eventually you go past this interpolation threshold and it starts to smooth out again. So that's called double descent. So this idea that you can have this extremely over-parameterized network and it can actually fit very well to the data. And this is actually a very new theory, and we're still kind of investigating it as a research field. This is going to help us understand regularization as well. So before I get on to regularization, let's just reflect on that no free lunch theorem and try to cheat a little bit. So specifically, while in theory we don't know anything about the data distribution, so we can't possibly know like what the best function is, whether it's the staircase one or whether it's the smooth cubic one. In practice, all of our data in the known natural universe has some very interesting repeated patterns that we can actually exploit. And those patterns come inherently from the laws of physics themselves. So signals in our physical universe are often repeated in space and in time. So for example, they have translational, rotational, and temporal invariances, such as, for example, blood cells that run through and flow through our bodies. They kind of, you can see these various symmetries in them. Take a look at like snowflakes, for example, or the face of the tiger. You've got this almost perfect symmetry down the middle. So just the patterns of the eyes are repeated on both sides of this symmetry line. And architecture itself, if you look at, say, Buckingham Palace, Just take a look at a building and you'll see architecture loves to follow symmetries. Windows are symmetrical, buildings, doors, bricks, there's so many natural symmetries that you'll see in the signals. And go inside Buckingham Palace and you'll see even more examples of symmetric chandeliers, symmetry in the carpets, symmetry in the books. You can even zoom out and you'll see symmetry in the planets, symmetry in the galaxies, symmetry in all kind of natural creatures. Data in the real world is filled of patterns which repeat. So this means we can actually design our neural networks and we can choose our functions from the hypothesis space, that space of all functions, such as to fit these patterns that occur in nature, that occur in the observable universe. And this is exactly what our brain's architecture has evolved to do. Our brain has evolved wiring to fit the natural signals, the visual signals, audio signals, spatial and temporal patterns very well. That's exactly what we do in deep learning. In fact, a lot of the functions we choose are inspired by our brain's natural evolution to fit these signals. So if you're interested, there's a reference here which talks about some of the similarities between physics and deep neural networks and why they work so well in physical situations. And the signals can also be hierarchical, so we see these kind of patterns and symmetries repeated over different scales. If we zoom right in, we see similar symmetries going into higher and higher scales. So with a design similar to cells in our visual system, convolutional neural networks are a perfect example of this. So in this slide we see an example convolutional neural network, and it's got these 3 input channels, or if you like, images. You could imagine this is like an R image, a G image, and a B image, red, green, blue. And then we have these 4 output feature maps. And we have this convolutional operator where we have a kernel which has 4x4 weights. So if you remember how a convolutional kernel works, it's where we just do a Hadamard product. So we multiply the values that correspond under the kernel, and then we add all of them together, and then the kernel slides over the input region to give the outputs. So the value of this pixel in this feature map here is where we multiply all the corresponding elements under the convolutional kernel and we sum those together. And for this case here, it's got, normally when you define convolutional layers in PyTorch, you have 3 main parameters, which is a kernel size. Normally we would have 3x3 kernels or 4x4 kernels, and a stride, which determines how many pixels you skip over each iteration. So a stride of 2 in this case is going to result in half the spatial dimensions of your feature maps. And then you have some padding, which is like just to pad around the borders to make sure your sizes are a bit more intuitive. Otherwise you're going to shrink sort of some of the values from your kernel each time. So, oops, sorry. So in this example, the convolution has 192 parameters and 4 bias parameters for each of the output features. And the 192 parameters is calculated by 4 times 4 for each of the kernel weights, which is 16 parameters. And then we have, that's repeated 4 times for each of the output features. So that gives us 16 times 4, which is 64 for each of the output features. And then we have to repeat that convolution operation for each of the input features. So you take 64 and you multiply it by the 3 input channels. So 64 times 3 is 192. And unlike linear layers, this is invariant to the size of the input image. So an input image of, say, size 4096 squared is still going to just have 192 parameters because the convolution just slides over, applying the same function. That's similar to how our cells behind our retina work. We have very similar functionality in the cells repeated over different regions of space. Whereas if you had a fully connected linear layer, then remember, like, every neuron is going to have to connect to all of the pixels in the image. So that means you're going to have, if it's a 4906 squared image, that's going to be 4096 times 4096 times 3 times 4 parameters just for the first layer. And that's already like 201 million parameters, which is like 805 megabytes of parameters. Whereas our convolution with just 192 parameters, that's like not even 1 kilobyte of parameters. So you can see how convolutions are super efficient, especially for dealing with large inputs where they can just slide the same function over space. And that's like what we see in nature. In nature, we see the same patterns repeated over different parts of space. You see like the texture on my t-shirt has this bumpy pattern which is repeated all over different space and so on. So that greatly generally reduces the number of parameters, and generally what we want to do is we want to decrease the spatial dimensions of our inputs, but at the same time we want to kind of increase the feature dimensions. So we want to and this is just showing like what a convolutional network actually learns to do. So normally we want to sort of take some images and reduce it to this feature representation. If you remember the definition of learning and deep learning, where we represent this complex high-dimensional data as these simpler form of data. And if you train like a classifier to predict whether it's the probability of a face, a dog, or a cat, and you train a deep neural network to do this, and you look at the outputs of each feature map, you'll see like it starts to detect regions where the eyes are and regions where the lips are to classify whether someone's a human, because it knows a human is some object which has eyes and lips and noses. So we'll actually learn detectors for all of these features. So the outputs here, if you inspect them, there will be like binary masks with a high response for the corresponding feature map where that feature is. And if you actually look at the weights that are learned in the kernels themselves, you'll see the weights correspond to say Gabor filters in the first layer, or filters which effectively respond to changes in edge, changes in texture, changes in, say, this is like a blob detector here, some oriented edge detector here, some kind of texture detector here you can see. And so in the second layer we start to build, we detect these features and we build detectors which use the already detected features from the layer before. So now we have like kind of square region detectors, texture detectors, these kind of curve detectors here. Maybe we've got like two blobs here, and these kind of interesting shape detectors in the second layer. Then in the third layer, the features use the detectors from the previous layer to detect more abstract things. And here we're now able to detect like eyes or legs, or maybe keys and tires, or tires of a car. So we've now got like a tire detector, or like an arm detector, an eye detector. And in the final layer, we use these eye detectors and leg detectors and tire detectors to build our actual final classifier. So we've now got our cat detector, a dog detector, a horse detector, a happiness detector. So you build and layer and you learn these deeper and more rich and abstract features. And this is kind of reflecting the idea that the patterns in nature are hierarchical. So deep neural networks are able to capture these hierarchies intrinsically. So it's very effective. Okay, the other type of function we'll often see is that we will see patterns repeated through time as well. So convolutional neural networks reuses the same parameters across space, as you've just seen. But what if we were able to reuse our parameters across time? Because we know that patterns occur in nature, the same patterns repeat over time. And recurrent neural networks do just that. They take as input a sequence of data, but for each element in the sequence, they reuse the same function over and over again. However, they pass some hidden state onto the next iteration, which allows the network to capture the sequential dynamics of the environment. And we're going to have a whole lecture dedicated to these, as they produce some very exciting results. So some researchers even go so far as to say these models are where AGI are going to emerge from. But one issue that has historically plagued RNNs, or recurrent neural networks, is as you backpropagate through them, through the sequence, the gradients start to sort of get weaker and weaker and weaker, especially in the earlier days. And this is called the vanishing gradient problem. So there's a few challenges with training very, very deep neural networks. The challenge that there's sequential dependencies, which makes parallelism more difficult. And also now it's mostly solved, but previously there was this challenge where the gradient started to vanish as you went down and down and down the sequence. So just the last one on function design. We can now go much deeper than we could before, because we can take there's this idea that emerged called residual networks, which is where we basically allow shortcuts in the neural network to occur. So we allow skipping over the nonlinearities And this gives us a clear, strong pathway for the gradients to backpropagate along. And there's evidence to suggest this type of residual behavior actually occurs naturally in the brain, as like some cells are able to have their connections skip over other cells, other neurons. And so this is like a residual block, and you can just sort of stick and paste these into a deep neural network to allow them to go much deeper without the gradient vanishing. It's basically just a block of a convolution, some normalization, and some nonlinear activation function, and then you've got another convolution and another bit of normalization. But so that's just the parameters of it. You've got the convolutions here in red and but then what you do is you add the inputs x in the forward pass onto the output of this block of functionality. So you take the inputs here and you add it onto the outputs of these two convolutions, which allows this kind of residual connection. And then you do your nonlinearity. And this basically, if you pipe these all together, now you've always got this nice clear path back to your inputs. And even if you've got 100 layers or many, many layers, and there's this clear signal for the gradient, so the gradient doesn't vanish as you go back. And people have recently shown this actually helps smooth out the optimization landscape as well, and you can click that paper if you're interested. So that's just kind of a quick overview how we're choosing our functions to go very, very deep, to be hierarchical, and to exploit natural patterns in translation. Okay, so now we've kind of got the main tools in our armory, so we can use these tools to build a deep and powerful neural network. But let's assume we've now just built a very powerful, extremely overpowered model. We can regularize it to ensure that it fits and generalizes well to unseen data. So before we formally define regularization, let's just think of an obvious way to do this, just by early stopping. So here is where we would train the model for a bit, and then we would have some validation data set, which the model has never seen before. We would look at the risk or the validation error as this starts to increase. And early stopping is simply where we would stop training just before that increase starts to happen. So we would try and stop at this dashed line here. So what we would do is we would save a checkpoint during training, like every minute or so. And then the second we see the validation risk starting to increase, we're just going to stop and use the checkpoint from just before that increase started to occur. And there's another similar approach called annealing, which is effectively the same thing, which is where, if you remember, we had that learning rate parameter. So we updated the parameters by moving them a little bit in the negative direction of the gradient by some learning rate, which determined how fast we learn. What we would do is we would just start off with quite a high learning rate, and we would slowly decrease the learning rate until the learning rate was 0. And when the learning rate is 0, it's basically just stopped. We would try and time it such that we would decrease it so it stopped at a sensible point before this risk curve started to increase. The advantage of that is it would allow you to experience a lot more of the data set if you've got like if for whatever reason you need to experience a lot more of the data in your application. So there are two very simple techniques that can be used to try and find a good stopping point before the model starts to overfit. So now, what is regularization? Well, regularization is just this kind of process where you add prior knowledge about your data or your functions or your risk, such as to reduce the generalization error. So we really want to just find any way or use any prior knowledge that we have about the data, the signal, the training to flatten this blue curve out. That's really what regularization is. So if we can lower this blue curve, for example, if we know that our functions are smooth, we can add some constraints to smoothen out our functions explicitly. That would be a form of regularization. Or even early stopping is regularization. If we know that it will start to overfit after a point of time, that's another form of regularization, which allows us to choose a suitable point before it starts to increase and overfit to the data. So perhaps one of the simplest examples is just data augmentation, and I'm sure you've covered these kind of things in the previous module, so I'll just go through them quickly. But basically this is actually a form of prior knowledge. So for example, we know that when you take pictures, people don't always hold their cameras perfectly steadily, so you can when training, you could just randomly add a bit of wobble to your cameras to reflect that inherent property of the photographs. That's going to give you more data, more images, which you know have this property. So it's going to increase your data set size. It's prior knowledge you're adding to reduce the test risk of it overfitting. However, it is prior knowledge, so if you add too much artificial rotation, this will be something you don't experience in the testing conditions, the expected testing distribution, and therefore the model won't fit as well. And a nice toy example of this is if you were to add 180-degree rotations to MNIST, that's actually going to change the class, so this 6 is going to become a 9. And so you're going to fundamentally change what's happening, so it's going to significantly decrease your model performance if you add such a severe rotation. Do you remember how in the first lecture we talked about Hebbian theory and synaptic plasticity, specifically how we're always forgetting everything and the synapse weakens over time unless it's constantly reinforced with new experiences? Well, that's a bit like the brain's natural way of saying only the relevant paths contribute, but nothing contributes too much. Anyway, what we would love is for some of the weights of our network to go to 0 and nothing to become too dominant. We don't really want the neural network to be making its decisions too much solely on one particular thing. So we want it to sort of share its weights and spread out its decisions over lots of signal information. And this can be done with Dropout, which is where we would basically randomly erase some of the hidden units with some probability. So we just kind of randomly drop them out and set them to 0, say 0.1% of the time based on some parameter. And this means that for a given neuron, say this one here, it cannot rely too much on any of its inputs. It cannot rely on this too much or this too much. So if you take the limit of it, it has the effect of the network has to spread out its weights across all of the neurons. It cannot just depend entirely on this neuron here because this might get dropped out at any one point. So it has to try and make its decisions spread out. And this actually has a very similar effect to, if you take the limiting behavior of this dropout idea as a form of regularization, to Tikhonov regularization, which is also called weight decay or L2 regularization. So like dropout, this is where we want the weight values to be close to 0 or close to the origin, so no single weight value is too high or too strong, and therefore the decisions get spread out over lots of evidence. So we do this with just by taking our loss function, L, we add another term controlled by this lambda parameter, which is just where we directly penalize the L2 norm of the weights. So if this weight value gets too positive or too negative, it's just going to bring it back to the origin. So this lambda controls the amount of this regularization we wish. So they're very, very similar if you take the limit of the two behaviors. And lastly, the last form of regularization, if you want to win prize money in Kaggle competitions, which are deep learning competitions where lots of teams participate, there's this, basically what you should be doing is building an ensemble of lots of models. So this kind of helps us summarize this whole lecture. If you want to really do well at this and win, and you don't care about doing anything clever, just team up with some colleagues. Have some of your colleagues spend all their time cleaning up the data, trying to make it representative of the task, fixing alignment issues in the data, fixing bias issues where certain classes are overrepresented, and designing bespoke augmentation procedures. And then you want to get as diverse a collection of the functions themselves as possible, so as many models as you can. So you want to train different deep neural networks, as many of them as you can, and use the largest models that you can possibly fit into your GPU memory. Then you train them all from scratch, just using enough regularization according to the validation accuracy. And then basically what you do in an ensemble is you just average all the results together. So for regression problems, you would just average everything. Or if you're doing some kind of classification, you would use a max voting procedure. So say you've got lots of predictions from all the different models. I think this is a car, a bus. You just take the max of what all of the models think it is. That's max voting. And that's really what an ensemble is. It's just averaging lots of models. So that kind of helps wrap up this lecture in terms of how you would win in a Kaggle competition. And it is a bit boring because most of the advances are just data cleaning and ensembles of lots of different models. So in summary, just reading the slide, designing architectures is really a scientific process where you have to choose the right functions which fit your data. There's no free lunch here. There there is some kind of process you develop, an intuition you develop as you learn about what the data is and what functions you have available in your armory, what are efficient and what have lots of parallelism and so forth. Choose your experiments very carefully. And so, for example, what do you know about the signal? Are the same patterns repeated over different translations? Are there symmetries? So you should be able to choose what you put into your network very carefully. Consider that double descent graph. Consider how well parameterized or under-parameterized or over-parameterized your model is. And just ask the questions, what prior knowledge can you incorporate into this? And always ask yourself, like, what does the task need? Are the features required by the task low level? Like, do you need to be distinguishing between textures and edges? So do you need to put all your capacity into the earlier functions? Or do you need to do things like detecting a happy kitten or a grumpy dog? So you need like a happiness detector. So you need lots of capacity in the later layers, which can detect those abstract things like grumpiness in a dog or happiness in a kitten. Okay, well that concludes this lecture. I hope you have a good week.